slide. So it's only based on my practical experience, so I'm not representing of any company. So then you can go to the next slide. Outlined, I will divide it into 3 parts here. I'm not really sure because it will take, if I talk through all of this, it will take more than 2 hours. Maybe I will just, you can ask me questions later on, but now I'm assuming that you have some basics on the heat integration concept, and then I'll then glance through the slides on the first part, and then I will also share a little bit on the industrial cases that I've involved regarding heat integration and also process optimization, process integration and as a whole. And then the quick tutorial on how to do this in practice. So this quick means it's really quick because I've been teaching this subject for many years already, and then that quick means like at least 3 days. So so this quick will be really quick. So next slide, please. So these are the references that I've always used. I think you can, you can buy this book or get a copy of a PDF or whatnot, but you have to buy it and then read it and then sleep with it. And then by the time you reach my age, then you know these books by heart already. Next slide. Okay, next slide again. Heat integration is only like one part of what we call now process integration, and then that process integration makes up like one aspect of what we call nowadays process system engineering. I'm not going to go into that detail, but the point is that to do a proper heat integration, I mean we have to see the systems or our plant as a holistic manner. We have to see it from the bigger picture. So we have our plant, and then how much is then the energy that it is consuming. So we can see it from the how much fuels that we are importing into our plant, and then how much is that the energy that we are losing to the environment. So these are the losses, and then the energy that goes to our cooling towers basically. So next. Next. So it's a process synthesis part. So in this process synthesis, I think it's onion diagram. So heat integration, if we follow this process onion diagram as a guideline, so heat integration is and on the 3rd layer heat recovery system, as you see in the onion diagram. So I cannot use my cursor here. So it's or I can if I share my screen, will it be better for you? Or because to me it's look like I cannot fully utilize or explain what I'm pointing at, what I'm talking about. Let me know, yeah, if it's better that I because I typically prefer to have it presented myself. So next slide. I hope that you have seen this flowchart before. If not, then this is then your first time. So number 1 is that we need to identify the hot and cold streams. But before that, the step number 0 is then to get the data correct. So this data can come from it should come from the field. Yeah, you have your plant data, and then from this plant data, you calculate the mass and energy balance. Okay, from this plant data, you calculate the mass and energy balance. So it may or may not be complete, but you have to do it. And then that's why we need to have like engineering judgment and then the knowledge of your process engineering. And then once we have the data complete and makes sense, in completing the data, we could also use process simulation to simulate the whole plant. The scope that we are going to do. And then once we get that, we identify which one is then the hot and cold streams, which I think you know. And then we specify what is then the delta T min approach that we would like to evaluate our we would base our evaluation on. And then we typically make composite curve and then grand composite curve in the 3rd box, and then we estimate the minimum energy targets. So we have that estimation, which I think you know this already. And then once we get the target with the data that we have, we can then identify any modifications that we think is reasonable to be applied, and then put that into our mass energy balance model, and then make this composite curve or the targeting, and then see if it can reduce the energy target. So if anything that I've said here doesn't make sense to you, just ask here. And then once we see any appropriate modification, and then we could also move on further to integrate with other process equipment. For example, we can we can do I don't know, maybe the heat that we release from the reactor, we can use it to generate some steam or whatnot. So that is then one of the things that we could do. And then we estimate the heat exchanger network capital target and then the total cost. And then we get, so for that specific delta T min that we picked before, we know then how much is then the capital cost, and then we know how much is then the associated operating cost. And then the theoretical procedure is then to get a new delta T min. Say, for example, your first delta T min is about 20 degrees C, and then you can increase it to 30 degrees C, or you can also reduce it to 10 degrees C, so that you can see what is then the effect of this changing in delta T min to your capital cost and then operating cost, and then you can then make a curve accordingly. So once you vary the delta T min from, I don't know, from 5 to 10 degrees C to maybe 50, 60 degrees C, then you will then see how much is then the cost is moving. So that's the theoretical part. But in practice, we don't do it because simply we don't have like an accurate cost estimation, and then typically this is done. Cost estimation is then done by people from the other department. And then the lastly is that there are many practical things that we cannot foresee. For example, we need to take into account the maintenance costs, and we need to take into account the foundation and structure. So these things are not, I mean, they have a separate department calculating this cost. So that cost can be significant as well compared to the or compared to adding one or two heat exchangers. And then once we when we select which delta T min they would like to pursue, and then we evaluate the how do you call it? Evaluate the modifications that we could foresee, and then we can then move on to design in the detail about the heat exchanger network. Go to next slide. I will skip this. I think you know about heat exchange. I'll skip this. Go on. Data extractions. Again, I will skip this as well because I think you would then know by now how to select which streams to use. Yeah. So I'll quickly. Hot stream is then the streams that needs to be cooled down, and then cold stream is then the stream that needs to be heated up. So identify the stream. Right. You get your data complete. And then identify the streams, and then you can then fill in this kind of data extraction table. The next slide. Some of the rules is that number one, if we have like because typically we have because CP is a function of temperature, yeah, and then we will have this curvy nature of the different CP values across the temperature range. So one way is then to linearize it in this manner. And then we also have like if there are streams mixing up together, so when we do the data extractions, we don't mix this stream. Yeah, we will then see whether or not these streams can be separately run, and see if there's any benefit from that. And then we don't extract the utilities because these utilities will be the things that we are going to design and evaluate later on. And then while we are extracting the data, we need to ask ourselves whether this data, number one, is then correct. Yeah, that's number one. And then the second one is then we need to ask ourselves, I mean, why is that data like that? You know, can we increase the temperature further? Can we reduce it further? So these things you can only answer if you have the process knowledge, if you have the knowledge of your plant. If you talk to the people who have knowledge in the plant, people who have been operating the plant, people who know what the process looked like, understand it, and then you can then ask these questions. Okay, next. Cold composite curve and then hot composite curve in the next slide. I don't think I want to explain that to you. Go on next. hot composite curve. So once we get this cold composite curve and hot composite curve, we will have this typical composite curve. I think this one I will spend some more time. So we can see typically this is then the composite curve, like how do you call it? Yeah, how people normally draw it. Yeah, so we have that the hot composite curve is then drawn in a red line, and then cold composite curve in the blue line, and then we know it's hot and is in the top. Yeah, because it's simply because they are the hot stream, the things that needs to be cooled down, and then the heat is then going to be transferred from the higher temperature level to the lower temperature level. So that's why we build the hot composite curve on top of the cold composite curve, simply because they typically have like a higher temperature, and then we need also to make like because this energy will then shift from the hot composite curve down, right, to the lower temperature level, if you see, because y-axis is then the is the temperature. So if we put the cold composite curve below it like this, that means there will be like delta T that can allow for heat to be transferred from the higher temperature region to the lower temperature region. So you have like overlapping region where the heat can be transferred. Next slide. I'm sorry. Go back to the first slide. When you see in this overlapping region, you can also see there are two, well, at least one. There are two. In this case, there are two non-overlapping regions. So that's the other one. The one is then the first one is then the one with the blue lines that is not overlapped or covered by the red line, which means that the blue line, that a cold composite curve, they still need some energy to cover it. Yeah, so that the temperature can go to where it is needed. And then the same goes with the red line at the down. So we have like can I use the, I don't know, yeah. Can I just share my screen, and then I will then explain it from my side, rather than because I cannot move. I mean, I cannot use. It's very handicapped me now. Can I do that, or it's not allowed? Yeah, because it will be easier for me. Okay, where were we? Oh, no. So this part is then what we call the region where there is a minimum heating utility. So in this case, it's 65 kilowatt. And this then basically the region where we have like a minimum cooling utility, which is 105. So what it says is that thermodynamically, if we have a delta min of 20 degrees C, so the distance, the minimum distance, if you look at the entire graph, the minimum distance is then 20 degrees C, which is this. So this is then our pinch point. Yeah, this is the pinch point. That means if we choose this delta Tmin of 20 degrees C, that means the minimum heat utility that we will supply is 65. We can supply more than 65, yes, but we cannot go below 65. Yeah, simply because if we go below 65, that means at least one of the heat exchangers that we're going to design, it will have a delta Tmin less than 20 degrees C. So that's basically what it means. The same goes with the cooling utility. So you could also, like I said, yeah, you can then select different delta T min. So you can then go lower, or you can go higher and higher. So the way to look at that is that if you go to higher, that means you are then having the minimum, like in this case, like 40 degrees is somewhere around here. So the way you do that, you just move it to the right, this blue graph. Yeah, you move it to the right or move it to the left to minimize the delta T between the hot and cold, and then you will then see how much is then the hot utility and then the cooling utility, the corresponding values, they will then change accordingly. In this case, I think you can see that if we increase the delta T min, we will then have to have a higher heating requirement, and also a higher cooling utility. There are various different situations, yeah, if you go along, and then this is also another step. If you see this graph, we use like exactly the same temperature. So in a way that we see the delta T, if we put like delta T 20 degrees C, and then we'll then have to stop where the two graphs at 20 degrees C. I mean the closest point between them is 20 degrees C. But then if you do this problem table algorithm, we will have to adjust the temperature. So this part, it will be easier later on if you want to see the pinch and then you want to see the grand composite curve and then all the algebraic calculations behind it. So the way it works is that we typically increase the delta, the temperature of the cold stream by half of delta T. So it means by 10 degrees C. And we also simultaneously reduce the temperature of the hot stream by half of delta T. So in this case, these two graphs, if you can imagine, it will then touch somewhere here at the 90 degrees C. So that's why we call this the pinch temperature. Okay. I will skip this because I think you know how to do that. Or I hope you know how to do that. And then we'll then see. So all of these algebraic calculations will then tell you that this then the 65 of energy that we have to supply, and then to the system, and then this 105 kilowatt is then the energy that we have to discharge from the system. So this is what I said. So we have the pinch temperature of 90 degrees C with the same value. It's just like they use different graph representation in this case, where we can see the two graphs are met at this pinch point. The importance of this. Okay, I will spend some time, at least 5 minutes on this. So this basically is then what we call like the bottleneck of the process, means that we cannot move this blue graph to the left, or we cannot move it to the left even further, because if we want to move it to the left, that means we are hoping to get this utility down, but apparently not. We cannot do so because it will then violate the thermodynamic. Yeah, any question? No? Okay. So the only way to do so is then by reducing the allowable delta T min, as I mentioned before, right? So, but in this case, if we say that we are stick to this the 20 degrees C of delta T min, so we are stick to the this 90 degrees C as the bottleneck of the process, and then if we see from here, we want to minimize the external utility, right? So that means we want to minimize this portion, right? We want to minimize these portions to be as low as possible. So the only way to do that is that, not the only way, there are several ways to do that. One way is then try to move these cold streams to below the pinch region. So that means if you can take away this part of the heat to be below, that means this part of the heat is not there anymore, and then you can then put this guy, you can then put this guy to there here to connect it. So if it is then connected to there, so that means we are losing this amount of energy, right? So that means we are now move the same amount. Say for example, this is A, and then this is also A. So we are now reducing 65 by A. So this is the amount that we reduce. And then by adding this to there, that means we are extending this a little bit further by another A, right? So if I draw the same A over here, so that means we are reducing, we are increasing the coverage of these blue lines more to the left in such a way that it will then get the same amount of A, so that the cooling utility will also be minus A. Okay, so this is then minus A. So that's how it works basically. And then the second option to do is that say if you can then pick any of the look into the process and then see if any of these processes you can then shift around this pinch temperature. So if you can then take, for example, this part, you can take this part to the top or somewhere here, I don't know, depending on how much you can pump the heat. Yeah, so that means if this is then B, say for example this is then B, so that means that means you will then add another B somewhere here. So if you add another B somewhere here, right? B somewhere here, that means you will then have to move this graph, this whole graph, you'll then have to move it to the right by B, which means that you will then have a lower amount of heating utility by B. So that will then be 65 minus B. The same goes over here. So because we are moving this from here to there, that means we are now, yeah, there's no more heat to be cooled in this area. So that means our graph over here is that move to the right by another B. So that means the minimum cooling utility is also reduced by B. So 105 minus B. So these are some of the important things about this pinch point. Just ask me questions if you still don't think that this makes sense to you here. And then there's also plus minus principle. It's basically what I have mentioned before. So go into the process, see if any of these process or hot streams or cold streams can be moved around the pinch point in such a way it will then reduce the minimum requirement heating and then cooling duty. Yeah. So we can only do these modifications, or what they call this plus and minus principle, if it benefits us from the energy perspective, or more importantly in practice from the cost perspective, which we have to take into account not only the operating cost but also the capital cost. So the use of that problem table algorithm, the shifting of the temperature, like I mentioned before, is then to generate this curve, the so-called grand composite curve, where we can use this to identify how much is then the, well, we can see the same number, 65. So from here to there is 65. You can see it there. And then from here to there is then 105. Sorry, you can see it here. It basically tells us the same story and as the targeting, but it tells us as well another deeper story. So it will then tell us what is exactly then the utility required, the utility level required. So the place option number one that we can think about is that I can put like 170 degrees C of steam at 65 kilowatts, to supply this. So because it stops there, so I can put like 170 degrees C. So if I put it on this graph, that means it has to be reduced by half of delta T, which is then 160 degrees C. So we can have this steam at 170 degrees C, and then we can also use like a chilled water from 5 degrees C to 80 degrees C to get the heat out of the systems. In this case, to get the heat out of the system in this line. So this is the one option, and the second option is that we keep the hot utility as it is, but we, instead of going the from 5 to 80 degrees C, which means that you can see that the this slope, yeah. Anybody can tell me what this slope means? So this slope, and then compared to this slope. So compared to this slope. So I will give you homework. Tell me what is then the difference. What is then the practical significance of this slope? Yeah, you can then later on put it in the chat. And then if you look carefully on the graph as well, we may not need the 170 degrees C steam, because the process that we want to heat is only from here to there, right? Yeah, from 90 to this part, because this part is what we call so this part is basically, we can build this part from process to process heat exchanging, yeah. We don't need to have any additional extra utility. So the additional extra utility can be supplied, from this point to there. So well, if we take like for example 150 degrees C of steam, put it on the graph 140. So that means we can, instead of having like 170 steam, we can use the 150 degrees steam. If these two steam levels have different cost price, yeah. If they have a different cost price, where the steam at 150 degrees C is cheaper, then we have to use this 150 degrees C to fulfill the heating utility. And then for the cooling utility, you can have like chilled water from 5 to 15 degrees C, and then the cooling water from 30 degrees C to 80 degrees C. So this is option number 3. And then there are plenty of other options which I'm not going to go. So pinched golden rules on the design. So we'll have like again we are not allowed, when we want to design this, we are not allowed to transfer heat across pinch. So that means this area, this overlapping area, is that area where process to process heat exchanges can be placed. Yeah. So and then the same goes with this area. Okay. So no heat transfer across pinch. That means you cannot hit this. For example, you are taking this part of cold streams and you are using heat from here. You're using it from here to this guy. That is not allowed. That is not allowed, because if you do so, then you will then see the complications that I've explained before. So what we have to do is then to stick with its own region. So this stream, it has to be heated by the stream in its own region, so by somewhere around this. So this should hit that guy. The same goes with this. We cannot, for example, we cannot cool down. Sorry, we cannot cool down this by that, or we cannot hit these streams by that streams as well. So this works both ways. Yeah. There's also the second rule is that there is no cooler above pinch. So because this up here is about maximizing the heat recovery as much as possible, we need to increase the amount of heat recovery as much as possible. That means we cannot put cooler to hit this stream. We cannot use cooler. If you do so, and then you will then see the complications that I've explained before. The same goes with the below pinch. This stream is going to be heated only by this stream, or this stream needs to be cooled only by these streams. So we don't need to add heater here. We don't need to add heater here, because if we add heater here, that means we are not using this energy. So that means this energy will then go waste to the cooling tower. So they will then, which we have to pay. Yeah. So these are 3 golden rules that that I think you know already. Just like a reminder. So this is then the grid diagram priority design. So once we get the target over here, and then we know that we have done the process modifications, we have done this plus and minus principles, and then we know that we can do much better in terms of reducing the heat, the minimum heating and cooling utility. So we go for the grid diagram to design the heat exchanger network. So we typically use this. Yeah, we typically draw it from the left to right. So left means the lowest temperature, and then to the right means goes to the highest temperature level. And then if it's like hot stream, I mean the arrow shows whether that stream is hot or cold streams. So in this case, I hope you know that this is then a hot stream, and then this one is then a cold stream. Yeah. And then we typically put the temperature, the supply temperature, and then the required temperature, and also we put like the MCP value, yeah, the heat flow rate value. And then we put the pinch point, you know, that 90 degrees C pinch point. So in this case, so the if you see this guy again, so many. So you can see that this is then the what we call like hot point, 100 degrees C. This is then the cold point, pinch point, which is then the 80 degrees C. So we put these 2 numbers into the grid diagram so that we know whether or not we are crossing the boundary. Okay. So some design rules. I think. So some design rules is that we start the design at the most constrained points, means because this temperature is fixed already. Yeah, this temperature is fixed already. 100 degrees C, 100 degrees C, and this is an 80 degrees. This is 80 degrees C. So this temperature is fixed already. So while this part it can while this is fixed, yeah, but then the slope from here to there, it can be very steep. Oh, sorry, it can be very steep like this, or it can be quite shallow, yeah, depending on the how much is then the energy that we are now transferring. So I hope you understand what it means by the slope here. Yeah, if not, then let me know. I assume now by now you know already what it means by the slope. Yeah, so this slope is very important. The same goes with the full slopes over here. Hello, any question? No. Okay, anyhow, so this guy is also moving in that direction because it needs to be heated. So this slope is also very important. Um, and then when we after we start from the most constant point, and then in the exchanging match, we can then exchange heat as much as possible. And then we can go through the examples. And then again, I repeat the same rules: do not exchange heat across the pinch, and then no cooler above pinch, and then no heater below pinch. This is not something that you have to memorize because there is no memorization needed for this. It's something that you I mean when you do this more often, and then you will then have it, and then you understand this, and then it is then in your heart already. So this one you can find this flow sheet in the a flow chart in any textbook that I put as the references before. Up until here, now it's okay. If you have any questions, just type in the chat. Yeah, I will try to go quickly as quick as possible so that we can have more time to discuss. So industrial cases, I'll go through this very quickly. So we have done here. This is then our heat exchangers in the plant. And then there are many heat exchangers. This is in the steam system, so that I make this mass and energy balance in Excel. So this is then one of our plants somewhere in China, where we do exactly we move heat from the like above the pinch to below the pinch, so that it doesn't consume the energy, or at least it reduces the energy. So in this case, you can see in this case in the grand composite curve, this part is like a very, how do you call it? It's very shallow, almost horizontal. So if you can then type in the chat what it means by this having horizontal line, or which equipment is doing this horizontal line, then that means then I can understand, and I can see you understand this. Okay, do you have any question? No? Okay. So if anyone can then type in what it means by this having like a almost horizontal line. So we think to ourselves, okay, can we do something about this, because this is then very close to the pinch point? Can we then change this guy from these locations to a little bit below the pinch point? Yeah, like 30 degrees C. Yeah, 30 degrees C. It's not that small, but it's quite something. In the end, we did change that. So we changed the column pressure in such a way that it needs not the medium pressure anymore. It needs the low pressure header. So from here we move it down to here. In this case, we reduce the amount of energy, which translates into some reduction in the amount of money. This is another chemical plant as well. So they have here they have where's that reactor again? Reactor. So they have another heat exchanger somewhere here, where it is not being used because I don't know. This was a second-hand plant. So there they have a second-hand plant. So you can buy second-hand laptop or second-hand car. There they have a second-hand plant, and then they use it. So some of the equipments they use it, some of the other equipments they don't use it. So when they did to do the revamping, so we increased the capacity to a certain degree, I think more than double at the time already. But because these are all like second-hand unit process equipments, they're all like designed very big. And then apparently one of the guys over here, they're not being used. And then we do this exactly the same step. and then we could see that if we do something, so we do all kinds of stuffs like this, and then we can then see so this part can be okay, the one that was not used before, we can then make a new piping around it, and then it is being used to recover the energy coming from the reactor, and then in that sense we can then reduce the amount of energy, because if you double the capacity of the plants, typically we will also increase the capacity the energy requirement by double or even more. So in this case, we can reduce the amount of energy required by less than not even by less than the double the energy. This is the latest project about heat integration that I did. It was 2020, 2021, 2021, yeah, 2020, early 2021. So we have fault heat exchangers everywhere in the plant, and then we would like to see if we have a different type of crude, for example, a light crude and then heavy crude. What makes the difference in terms of the energy consumption, and then can we do something in the plant? So this is then the heat exchangers that we are working on. And then you can see in the legend over here. So if you see something like this, that means something like this. That means this is then existing heat exchanger. But I put green over here. That means this exchanger particularly, it has to be cleaned. And then all of these reds, we typically use these reds as hot utility or heaters or fine heaters or boilers, and then these blue ones are the cold utilities, means it's chilled water, refrigeration, so cooling water. In this case, it's cooling water mainly. And then they are already like in the plants. They know people. They make a long list of exchanges that are on the fault list, and then based on the data that we have, we compare the current performance, because we do the mass energy balance around the exchanges, and then we compare to the design performance, and then we know that they are not functioning as intended. So the overall heat transfer coefficient is much lower than it was designed for, and then we know that they are like fouled. So what we identify over here, they are indeed fouled, and then the same as in the what's in the list. And then there are another options on the to enlarge. So in this case, for example, this exchanger, we can enlarge this, that exchanger, we can enlarge that in such a way that we can recover more energy. So these are some of the options. And then the blue ones like this, you can see like a black circle and a black line. So these are existing heat exchangers. And then the blue ones like this, these are the one of the new exchanger that we want to add into the system. If you see that this is number 5, number 8, number 2, and then this number 1. So these are all options. So in the end, we have at least 8 individual options. Yeah, 8 individual options, and then we also have like many combination options, combinatorial options. So where we, for example, in this case, we don't implement option number 1, but we could also implement option number 1 and 2. So that's another options. So in the end, when we weigh them, we put this into the process simulation to see how the system behave, because refinery in this case, it's all like what we call it is a crude distillation unit, yeah, and then this is obviously the crude preheating train. So they are like they're connected sequentially. So if we do some recoveries at the front, and then it will then disturb the whole entire train up until the. So when we do something in the front, and then we have to simulate the whole CDU to see what is going to happen at the end. Yeah, because any modifications that we think we have accomplished over here, or we designed over here using this sheet, it may not be what we expect from that. It may not be the end result once we get the whole simulation, the whole option simulated. Okay, so once we do the simulations, and then we can calculate the benefits like operating costs, the reductions of the fine heater. In this case, this is then fine heater number 1, fine heater number 2. So if we can do modifications and then reduce this duty down, and then we can then calculate as well how much is then the new exchanger cost, and so on and so forth. So then we can weigh in which one is then which options or which combinations of option give us the best cost benefit how to call it, implementation. So if we then plot this cost, and we can see the capex, and then we can see the payback period, and then I plot them over here. So we could see that option 8 is then having the lowest capex and then the lowest payback period, and option 1 plus 3 plus 8, it's the second rank, and then option 1 is also doing very good as well. So and then these options, they are not so good in terms of the capex, and then in terms of the payback period. So this is basically how we evaluate which heat integration project that we're going to implement further on. Yeah, because if we say that I want to implement project number 8, so that means project number 8 is over here. So we will have a new exchanger from to recover heat from this stream to that stream, in such a way that it will then reduce the energy consumption in this heater. So we need to know, yeah, how much it costs, and then we need to know where it is going to be located in the plant, and then this location also will create we'll need to invite people from the civil, from the structure, from the piping, from the maintenance, and so on and so forth, so that they know that these implications will come, and then they know how, and then it will not then be burdening them. For example, if I put this in a high platform, that means we need to ask the civil or the structural engineer whether that platform can withhold this additional new exchanger. And also we need to look on the field whether the maintenance people can just take out the bundle so that they can do maintenance on this particular heat exchangers. So these two aspects are things that we cannot easily quantify when we do the like I said, the theoretical delta T min delta T min versus the capital cost graph. And then I did another two. I mean, from this process integration, there's also like a freshwater and wastewater minimization. So this is then the Petronas fertilizer plant in Kedah, where we did also process integration project on that. And then there's another plant in this is actually if you know LG, you have mobile phone LG, right? So LG has also chemical plants, and then this is then the one of their plants in South Korea. So we do also this kind of study. Nonetheless, I think I'm now okay. So about 1 hour. If you have any questions, just type in, and then we'll see if I can finish this in half an hour. So then we can have more time to questions. Let's do a quick tutorial, because that's what Dr. Shafiq asked me to share with you. So I will repeat this work pattern again. You need to now define the scope of your study, yeah, because like I said, this heat integration is part of the study, what we call process integration, where we see things from the system perspective, from the holistic manner. So we need to understand the scope of the study. So if it's like your plant, that means this then your plant, for example. So all the reactors, heat exchangers, columns, whatnot, they are here. So this is then your raw material, and then this is then your product, yeah, this is then your waste, and so on and so forth. And then you have also like fuels coming in. You have fuels, you have and then you also have like this then your cooling tower, for example. So you need to understand. So if you then make this boundary, so you can then gather knowledge on how much is then currently that you are removing to the environment, how much then fuel that you are importing into your plant. So from here you can have a sense of okay, now our base case is this. So with this value, that the heating requirement and then the cooling requirement, and then you can then make a mass and energy balance around this plant. Yeah. Point number 2, make a mass and energy balance around this in your plant, to way that you can then compare, yeah, use that number and then make the composite curve like I mentioned before, and then compare that composite curve results, the targeting, how much is then the minimum utility requirement, how much is then minimum hot utility requirement, how much is then minimum cold utility, and then you can compare cold utility with this guy, and then you can compare hot utility with this guy. Yeah, and then you can then have a sense. So now my base case is this much, and then my energy balance, the minimum is then by this much, and then the difference between them is then your area of improvement, so to say. Okay, so that's the targeting, and then once we know how much is then the area of improvement, we can then identify opportunities, like we said, and then put this opportunity back into the simulations or your mass energy balance calculations, and then evaluate the options whether you have to make more than one solution, like I showed you before. So we have like at least 8 or even dozens of solutions if we can think about the combinations of them. And then once you calculate the technical aspect, evaluate the technical aspect, whether it can be applied, how difficult it can be done, and so on and so forth. And then you can then calculate how much also the economic cost of that, the operating cost, the profits or the benefit that you will get compared to the capital investment that you will have to fulfill. And then you can then make a ranking like I did over here. I think which I did, make a ranking. So then you will then present to your boss saying that, boss, this is then the ranking number 1, the best one, ranking number 2, number 3, and so on and so forth, so that they know the implications of I mean you are coming to them with the data, arguments based on data, which is always compelling. And then if any of these options are agreed, and then you can then implement the selected option. So this one, typically we do it in the next phase of the project. So we do this like a conceptual basis, and then we do like an engineering if one of these options are accepted, and then we go to the engineering phase where we make more detailed analysis and calculations. And then if we see that the economics is still valid or still okay, and then we move on to the construction. Okay. So everything here, everything's over here is basically this one, and then okay, let's do an example. Discard. So I will just make a dummy case. I have made a dummy case apparently. So assume now you have a plant. Yeah, your plant is that in this case we are making DME, dimethyl ether, from dehydrating methanol. So you have methanol coming in. You have methanol coming in, and then you take water from that methanol. Yeah, if you put two methanol in, and then you take water molecules from that two methanols, you will make DME, dimethyl ether. Yeah, you can Google this process. It's very well-known process, and then it's the only process that is available on the field. So we have methanol coming in, and then there's some unreacted methanol as well coming in, mixed into this storage tank, and then we pump it to the reactor. And then this reactor, it requires pressures about 15-16 bars, and then the temperature of about 250 degrees C. So as a base case, so I just put a dummy case, so assume that this is then your plant. So as a base case, we have a room temperature methanol, and then we want to heat that up until 250 degrees C, and then this is then the amount of energy that you will need, about 4.4 megawatts. Yeah, 4.4 megawatt is then the amount of energy that you need. So how do you know this? You make the mass balance. Yeah. How do you make the mass balance? Well, you can do it like process simulations, getting data from the field, do the process simulations, or getting data from the field and then make your own Excel sheet or whatnot. So for sure, you have to make the mass energy balance simulation. And then we have the conversions, and then roughly about 80% of the methanol is converted. So that means 20% is going to come back. So this is then the 20% of methanol unreacted over here. And then this reaction is exothermic, means it will then release energy. Yeah, if it then release energy, and then this reactor is like fully insulated, so we can assume that this is adiabatic in nature. So the temperature going out will be, is it going to be higher or lower than 250 degrees C? So it's something that you can write down in the chat, yeah, if you know the answer. So nonetheless, once we get that temperature, and then we will then have to cool it down because we want to separate here. So in this outlet stream, we have like the unreacted 20% of methanol, and then we have the DME and water as well. And then the I don't know, maybe later on you will then be taught on how to design a process like this. But nonetheless, if I were to teach you, then I will then ask you to get all the properties of the chemicals that you're going to deal with. So in this case, we have the methanol, water, and then DME. And then once you know the properties, one of the properties is then the boiling point, and then you can then sort them from the lowest boiling points to the highest boiling points, and then you will then know that DME is then the lowest, is the one with the lowest boiling point. So it goes to the first column, and then you know that DME is going to go up over here. So this is then DME, and then what goes down is then water and methanol, and then they are being separated in the second column, and then where water goes down, yeah, and then methanol being about 60 degrees C, it goes up as a distillate and then being recycled to the steam, to the tank. So we have now this is then the stream to be heated, so this is then cold stream, and this is then the stream to be cooled down, so that means this is then hot stream, and then in the distillation column we have in this case we have a cooler over here, so that if we have a cooler, so that means this stream is a yeah, if it's a hot stream, I'm not going to ask you to put the answer on the chat. So it's going to be like a hot stream, and then this one is then we are taking heat from the environment or from the steam or from the external. So that means this stream is then the cold stream. So we have cold streams, hot stream, cold streams. The same goes with here with this one. So hot stream, cold stream, and then this one because it goes to wastewater, and then there are some traces of methanol always. So we want to we don't want to like how do you call it, pollute this wastewater environment with the very volatile methanol. So we want to reduce the temperature further from about, how much is that, from about 160 degrees C to yeah, 50 degrees C, so to say. So at least below the or close to the below the boiling point of the methanol, so that we know that methanol is not going to be evaporating. So this is another hot stream. So we have how many cold streams? We have cold streams 1, and then another cold streams 3. So we have 3 cold streams, and then we have 1, we have 2, we have 3, and then we have 4. We have 4 hot streams. Yeah. Again, I repeat, in this particular case, very simple one. We have 3 cold streams. 3 hot streams, 4 cold streams. And you can sum them all, yeah. You can sum this for hot utility, for example, you need to have like 4.4 megawatts, and then this one is also 0.8 megawatts. This is then 0.8 megawatt as well. So you can sum them. So in total, you have 4.4, 0.8, 0.8, 0.8, 0.8 means 1.6, 1.6 plus 4.4. So it's about 6 megawatts of hot utility. Yeah, so in this particular case, your existing plant, it consumes about 6 megawatts of hot utility, and then you can do the same with the cold utility. Okay, so that sets your base case, and this is then the base case, and then in your model. And then once we know, yeah, so what we have done so far, we collect the data, we calculate the mass and energy balance, and then we have identified as well the hot and cold streams, and we have identified the base case of the current energy consumptions for hot utility and then the cold utility. So we have done 4 steps: collect data and do the base case, collect data, and then make the mass balance, and then identify the hot and cold streams, and then yeah, calculate the base case. So the 4 steps. So once we know which streams that are hot and cold, and then we can extract the data. So we know the flow rate over here, and then we know the in and out temperature, for example, so that you know how much, yeah, I mean to to which extent that you want to increase the temperature or decrease the temperature, depending on which trim that you're talking about. You get that data, and then you can put it into many different forms and many different tools. And then one of them being, in this case, what they call like Aspen Aspen Energy Analyzer. What they call Aspen Energy Analyzer. So there is a template for that, which you can find in the installer folder of Aspen, and then you can then key that into the I don't have it here, so key that into the this one. You can key that in um, 1 minute, yeah. So you get the names of the streams, and then you can then key in the inlet and out temperature, MCP, delta T, and then the enthalpy, or just simply these three, basically these three. And then so that's one, and then you can then import that again into this HYSYS, or you can go to HYSYS. Nowadays HYSYS has this energy analysis, and then you can then I think there's an option over here, which I did already some time ago, and then you can then you can then move this, create, which I did here. I don't remember how now, and I don't want to dig deeper showing you how, because it will then consume lots of time. So nonetheless, that's how I did that. So I did that automatically from Aspen HYSYS to Aspen Energy Analyzer. Make the data nice. For example, there are some 384 point something something, so I just put 384. So all there is like one the accuracy is then 1 degree C. So in this case, so if we go here, we go to composite curve, we can then see how the curve looks like, and then we go to the grand composite curve, and then we can then see how the graph looks like. And then that's what we know from the we know then the pinch point somewhere here, and then how much is then the hot and cold utility. And then after this we go to the heat exchanger, the grid diagram of the exchanger network. So typically we could do like it will then show us, typically it will then show you this, but then I need to know, like I mentioned before, when I explain about the grid diagram, I need to know where the pinch point really is. And then I put like the lower temperature on the left and then higher temperature on the right. So if you can see, it's not really handy. You can see it's very small, right? And you cannot scroll in and out, so you don't know. You cannot use your scroll to zoom in and out, so it's very small. And then what you could do is only like increase this by this, and then it's not really and then if you want to see somewhere on the left, and then you go up again, you cannot use scroll, so you go up, and then something like this. So you can see, for example, basically it has only like one pinch point, but in this energy analyzer, it takes into account, because I've defined here my utility. I've defined here my utility, and then that utility is then taken into account, and then they then put this utility temperature. I define utility 30 degrees C and then 35 degrees C of air, and then the same goes with the heater over here. So heater over here. So I have high pressure heat steam, mid pressure steam, and then hot oil as options. And then based on this, the temperatures of the utilities that we have set, and then they have somehow they have like, not somehow, they use the additional data of utility temperatures into this calculation, and it will then make them the additional pinch point like you see over here. So this is basically, sorry, see, this is not so handy. Yeah, so this part is basically the pinch point of utility, cold utility to the system. This is then your process pinch point. You can see 164. If you see what's that stuff, see about 160 something, so that's your 164. This is your process pinch point, and then this is then the pinch point corresponding to the presence of the hot utility. Yeah, okay, so don't be intimidated or surprised by this. This part is basically the one that I mentioned to you, the process heat utility. So this is not so handy. people on the field, we don't use this. Yeah, so we have to tick this and tick that, and then scroll this and scroll that, and then the way it works is just to give you an idea. This is then typically here. So this is then the whole system as it is designed now. Means we have a condenser, for example. Yeah, we have condenser. You can see here, condenser column 1 and then condenser column 2, and then they are cooled down by, well, it should be like cooling water, but it's how air anyhow. It's a mistake. So they are cooling down from 125 degrees C to 124 degrees C using this heat exchanger, and then exchanging heat of I double click this exchanger, so you can see from 125 to 124. So it's tied up. That means I will then use this temperature. Using this temperature means I know how much energy that it is being used. So this duty is then calculated accordingly. And then obviously, because this is then your initial temperature defined, and then it will then calculate for you what is then the outlet temperature of this air, so to say. Okay. You can see yeah, the delta of the cold end, the hot of the hot end, which is also calculated. I don't know why they are blue, but nonetheless they are calculated. And then also the heater, we have this stream. So the one that the boiler, reboiler 2 in this case, reboiler 2 is then being heated up by this steam, and then this is reboiler 1 heated up by this steam, and then we have this one by hot oil. So this one, so the guy, so the one from the stream 2 to 5, see, stream 2 to 5, which is okay, that's okay. Stream 2 to 5, just to give you an idea, yeah. Stream 2 to 5, it is being heated by hot oil because we need to have like a 250 degrees C, and then I don't have steam at 250 degrees C. So like maximum is this number. So hot oil, I can put like 280 degrees C in this case. So it is then used to heat up the 33 degrees C of methanol from the tank all the way until 250 degrees C of methanol. Yeah, well, this is like a simple approximations. Typically, we could also use like a fight heater. So hot oil in the first few megawatts, and then the next fight heater, because it can then for sure it will then reach much higher temperature than that. But this is just an example. Yeah, this 280 degrees is also very special heating oil practically. So this is the way we set up the base case. Yeah, the existing heat exchangers, and then as you can see over here, so you know that this is then the pinch temperature, and then you can see that this stream is exchanging heat from the lower parts or below pinch region to the upper pinch region, because this hot oil is all the way on the right part of the pinch. Yeah, this is then the pinch point. I'll put this to you so that you can see what I'm talking about. See, so this line is that line, and then what we are doing over here, so all of this energy from the lower to the right, all is then heated up by the hot oil. So remember, there are two rules. Yeah, if you know, you can quickly type what are the two rules that are violated by this arrangement. Yeah, I'm not going to tell you now, but type in on the chat what are the two rules that are being violated by this existing arrangement. Okay, so this is one, and then the one way to visualize it, and then see if you can then work around it, and then you could also like enter air-to-fit mode, and then then invisible. Yeah, so it's like some invisibility on the temperature, because the delta T min is then 20 degrees C, and then you've seen already in this case. Sorry, which one? Yeah. There is some invisibility, it says. Oh, unsatisfied stream. So there is no invisible heat exchanger, 0, heat exchanger calculated 0, but there is one stream not satisfied, which is in this case the MP stream. So so it is this I just put it there so that you know that we have that options. But if we have that options and then we put it into this file, and then Aspen will say that this guy needs to be satisfied as well, which is yeah, I mean we don't need to. So in practice we don't use this because of the complications. I mean the difficulty in navigations. We typically use the manual one. Yeah, if you can do so, like I mentioned, like I put into the like I used in this example. What is that stuff? See, I mean the original design. I mean the original heat exchanger network was much more complicated than this one. So this is just a simplified version from the paper that I from the paper over here. Okay. Oh, this is then the paper. I'll just show you. So from the paper over here. So simplified versions of the existing heat exchanger network. So this is then the one that is copied into this presentation slide. So what we do, again, I do the same. Put all the streams lower temperature level on the left and then higher temperature level on the right, and then we can then, for example, in this case, we know that for example, currently this guy at 33 degrees C and 25 degrees C, it's heated like this, and then there are many also cooler. Yeah, so for example, this one's also reboiler because we have existing reboilers, right, using hot oil, I guess, or with whatever means that. But in this case, I think it was with steam and then hot oil. But it doesn't matter in this case because we're not designing with which utilities that they're going to do. But we know we need to, by doing this exercise, we know that they need to have a certain amount of duty. So and the cooling tower, let's go cooling tower, the condenser, and then there's another condenser, and then we have sorry, we have another cooler, right? So we have one cooler, another cooler. So basically, this is then the outlet temperature of the reactor. So 384 to 100 degrees C, which is this guy. Is this guy? So 384 to about 100 degrees C. So that's the guy. So there's a cooler, heater, and then cooler, and then heater. So that's basically the scenario over here, which you already calculate how much each of the duty, right? So so in this case, I think I need to show you something before we go on into this. So instead of having this guy using Aspen Energy Analyzer to calculate for us the targeting, like I showed you, you could also Google, and then I googled a little bit, and then you can have. I've been using this. This is the one coming with one of the books that I put in the first slides. So this is then the slides coming from that book. So if you Google this from IChemE, you will see this file. And then here we do manually. So I name it properly. Yeah. So stream 2 to 5, stream 6 to 8. I think you know what, stream 2 to 5 already, and then so on and so forth. And then inlet temperature, outlet temperature, and then how much is then the heat capacity. If you know the duty, and then you can do some mathematics. And then using the delta T of 20 degrees C, you go to the problem table algorithm, and then you will then see the hot temperature is then 50 degrees C, it is then 33 degrees C, hot utility minimum is 800, maximum is then 1000. So remember that we calculated already the base case of hot utility. Yeah. So the base case of hot utility was about 6 megawatt, and then apparently with this 20 degrees C, you could go down to about 1 megawatt or 0.8 megawatt or 1 megawatt. So there is from 6 to 1 megawatt. That's a 5 megawatt difference that we can then how to call it? We can then save. So that 5 megawatts is a lot of money. So that's the potential, which is a lot. And then you could also see the composite curve. Here looks like this. It looks a bit different. It looks different. So there must be some data that I put wrongly here. I put the data wrongly. What's that stuff? See, the composite curve. There's something wrong. I mean, the shape of this is correct, but there's some. I think some of the units are not okay because in Aspen there's this kilojoule per degree C hour or something, that I must have done some mistakes in these calculations. But nonetheless, how do I know if this is wrong? Because I redo this several times, and then I also find another Google Excel. You can also Google this, yeah. And then I put the same inputs, and then it gives me the same results. Sorry. So it gives me the same type of curve, and then I think in this case it shows you how much I see. It shows you that the same amount of energy is being used. So I thought I did this right some time ago. I don't remember anymore. But nonetheless, I think you get the point. How we do this, how we get the target, and then when we get the target, we know that at least now in this case we can then you can then save about 5 megawatts. Yeah, very optimistic, but let's see if we can then save 5 megawatts. So now in this case, let's see, the target is then to get somewhere near. Much time do I have left? Okay, for half an hour to go. So these are all the existing scenarios. So let's see. Pinch point is about like 43, so 53 for the hot, and then 33 for the cold. So this guy is started at 33. We can see here, these are all hot streams. I put them on top part of the diagram, so it's also a way, or my way, to help visualizing this so that we can have a consistent visual. So hot stream on the top, cold streams below, and then we can see well, this is not it's not like fully correct, but at least gives an idea where this temperature are located. Say for example, see this guy is I mean it's passing through the pinch point, and then it's losing the energy into the cooling tower. So let's say instead of losing the energy, removing all of the energy, I'll just remove the energy by heating up this stream, yeah, for example. So I put it there, I just copy it. So one stream is then using one side of the exchanger, and then the other stream is then using the other side of the exchanger, the other stream. And then obviously I'm not going to put it there because if I put it this cooler over here, so that means I will have to, because this stream is going to be cooled down further until 50 degrees C, and this violates our delta T min. Yeah, so instead of doing that, I will then put it over, and then we just simply need to calculate how much is then the temperature here if needed. But in this case, we want to stick to the rule. So we'll say we will use the delta T min of 20 degrees C. So that means this temperature over here is 50 degrees C. Yeah, I will just put this to the left. So this temperature is 50 degrees C. This part is 53 degrees C. So this is then 3 degrees C difference. So if this is then 3 degrees C difference, assuming constant Cp, so that's very important to know the profile of your Cp, the Cp of your stream. So if you assume it's about 3, means constant, so it's about 3 times 3, so about 10 basically. So this guy, this energy, so the existing how to call it, yeah, the existing heat exchanger, it can be reduced to about, yeah, how much was that? About 10, right? It's about 10 kilowatts. Yeah, can you get my point? Yeah, so 50 to 53, that's 3 degrees C, and then this is then the MCP is then 3.2, so 3 times 3, 9, 10, whatever. Okay. So about 10 kilowatt. So this is 10 kilowatt. I don't remember how much was that. So previously I will then put over here so that all we know now about 10 megawatt, and then previous. So we can calculate that basically. Yeah, we can, or if we are too lazy, we can just go back always to our mass balance. But assume that we are quite diligent in this case. So 50 to 168, so that's about 118, right? Am I correct? Yeah. Well, let me know if I'm making a wrong mistake. So 118, 110, I make it 120, or I may make it 100, yeah? 100 degrees C, 100 degrees C times 3, so it's about 300 degrees, 100 degrees C times 3, about 300 degrees C, about 300 kilowatt. So it's about 300 kilowatt of energy. So previously it was 300 kilowatt of energy that we destroy to the cooling tower. Now, by exchanging heat over here, we can see that we are, well, it's about 10 kilowatts. So we reduce this coal utility from 300 to 10 kilowatt in this particular case. But then how much that leaves us over here? How much that leaves us over here? So if we say that 50 degrees C to 168 degrees C, how much is that? 50 to 168, how much then the delta T? Yeah, it's also roughly about the same one. I mean, about 200 something. So assume 100, yeah. I mean, you have to do this calculation correctly. So assume 100 and then times 3. So it's also about 300. So which is the previous one, yeah. Because if you compare this 300 to 10, this 10 is almost nothing. So now we can say, so this is then about 300. So 300 kilowatt that we can recover in via this exchanger. I'll put it over here so that it doesn't. So 300 kilowatts, and then this 300 kilowatt is then transferred from here, from this stream to that stream. So if this is then 300 kilowatts, and then we 33 degrees C, and then we know it's about 20 in average. I mean, you have to again in detail. And in this case, in the grid diagram evaluation, I forgot to mention this. So in the grid diagram evaluations of here, it's because it's a quick calculations. So here we assume a constant CP typically. So we will do like a two-step evaluations over here. We see what is possible using this assumption of constant CP. So once we get this option, for example, we get these options, and then these options will then have to be put back into the existing simulation. Okay, so let's see, how much time do I have? Okay. So if it's 300 kilowatts, that means 300 kilowatt divided by 20, it's about, I don't know, about what? About 15, right? So 15. So this 33 degrees C is about 15 now. This temperature is about 15 degrees C plus 33. I hope you can follow me. Yeah. 300 divided by 20 is about 15. So 15 plus 33. How much is that? 15 plus 33 is about 48, right? About 48 or 50 degrees C. So 48 degrees C. And then by now, you know that you have a 15 degrees C, 300 kilowatt over here. So that will then reduce this duty by 300 kilowatts, right? So this duty will be reduced by 300 kilowatt. So now let's see how much is this. So if it was like from 33 to 250, about 7 megawatt or something. Sorry, 33 to 250. How much is this? Well, I don't know. Yeah, it's about 220 degrees C, roughly 200 degrees C, and then multiply by this guy. 200 times 200 is about that's about this 4 megawatts or something. So it was about 4.4, say 4.4 kilowatt, and then this is then minus 300 already, right? Because we are now removing the 300 from here to there. So we see already like a reductions of energy into for the fire heater. And then we could also see, well, there's another big streams over here. This is the one that I forgot to mention to you, because if we follow blindly the heat I mean the typical textbook way of designing things, we will for sure first, number one, we will look into this, because we will design from the most constrained point. Yeah, so theoretically this we cannot allow this to be violated. So that's why theoretically we will have to obey these rules. So that's why I mean unconsciously I started with this kind of arrangement. But if we see this stream is basically that stream, the streams that needs to be cooled anyway, and then this is like a higher temperature, while much higher than 68. So this 168 is basically something, I think it is one of the 168 is, oh, this guy, see, 168 until 50. So that's 168 until 50, that's the guy. If we look at the process, it's more preferred to use up this energy first, and then if there is something remaining, then we'll then use the heater, or we'll use this. But in our case, the strength of the grid diagram as well, it tells you, well, you can use this directly, but you could also use this because then at a lower temperature than that one. Yeah. By looking at the flow sheets like this, we may miss this, but if we look at the grid diagram like this, you know that this guy is more suitable at the lower, at least at the lower part of this stream, and then the bigger the higher temperature part you can use the other stream. So now if I copy this and then put it over there, I'll put it over here so that it will not then confuse you. I'll put it somewhere here. Yeah. So now, do we need to have this? Yeah, maybe not. I don't know. But then if we see this, the lower temperature that we need to have is 100 degrees C, while this guy is 48 degrees. So that's 50 degrees C difference. So that means there is no need even to use cooler for this guy, because we can design it from to achieve 100 degrees C. Suppose that we take this out. Yeah, and then we would like to maximize the use of this energy. Yeah, because we want to maximize the use of this energy, because this stream, apparently, if you go back to if you make the composite curve, if you make composite curve, that stream, that 384 degrees C is this stream. So it's very big stream. So we need to maximize all of this. We need to maximize all of this. So we can maximize them, yeah, based on the so you can based on this graph, this whole 384 degrees C stream, we can maximize all of them. So that means in this case, we calculate how much this is. So 100, 384, it's about 284. 284 times 14, I don't know how much that is. Somebody can then get the calculator, and then 284 times 14 is about, see if this is a 300 times 15, it's about 40 something. So it's somewhere about 4. So if we say this, then if we say that's about 4, it's about 4, right? So so assume that this is about 4, or even more than 4. It's something that you have to calculate yourself, yeah. So if this is then a 4 megawatts, and then it's then going to be used over here, and then you can calculate how much is then the temperature over here. So it on the right. So you can calculate how much the temperature over here. So it's 4 megawatts. 4 megawatts divided by 20 is about 200, right? So 200 times plus 50, 48. So 248. So almost there. So it could also be there. I don't know. So it depends. So now you have all of this stream entirely cooled down to 100 degrees C, and then this stream. So you may or may not have this. So now I put this minus, sorry, minus about 4,000. So it's about 100 left, right? 100 left. So if we do more accurate calculations, it may so the 100 kilowatts may be gone, or this go to 250 degrees C. So this is something that at least now in this case we have option 1, option 2. So I will then say this option 1, this is option 2, or the other way around. It's up to you, or you can do both. So now you have option 1, option 2, two options, and then a third options by combining them. Yeah, so there are 3 options at least, practically speaking, that you can then say to your boss. And then now assume that we have used up all of the options, and then what should we do now? So once we get this simplified design, we can go back to our here, and then we can then add, because this stream is going to be used to heat up that this guy, yeah. So we will add flow sheet stream, and then we can add this heat exchanger, because we're going to use this stream, right? And then we will then cut break connections. A minute, yeah. Doesn't want to cut. So I will cut this, and then I will also cut I will also cut this. So that means I want to put this into here, It'll take some time somehow. No. So I will then do this. Is it hot stream or cold stream? Minute. Tube inlet side. Oh, it doesn't matter. Doesn't matter in this case. So we put it over there, and then the yeah. I have to think. And then we put it over there. And then over here we will then use this and put it over here. So that we know. Put it over here, and then put it over there. Okay, so now if we look at this, we need to have a certain degrees of freedom. We need to know how much we can then recover. We have connected the streams like this, and then we need to know how much then we can recover. For example, yeah. Now I'm doing it from this side first. Yeah. I should have done it from this, but in any case, looking at the time, I think you can do this on your own later on. You can start from here and then put it over there. In this case, I do it that way, so that for example, we need to know unknown delta P. It says so. Yeah, then we have to specify the delta P. Specify Pascal. It's also another 10 kilopascal because this is like a new heat exchanger that we would want to design. So you could, typically we would design it like at 30 kilopascal on the shell sides or even lower. But on the tube sides, we can also do the 30 or 50 kilopascals. But for the sake of argument, in this case, fine. Yeah. All right. So how do you call it? So we need to specify again what is the temperature over here, and then we know that this temperature, because I have designed it until it is cooled at 100 degrees C, but then so that means this temperature over here, we need to make sure that it is at least above 10 degrees, above 100 degrees C. Yeah? So it means if this then 100 degrees C, that means this exchanger is not going to be used anymore. So which means this is not going to be used anymore. So if we do so, we'll see what happens. So that means I have to then reduce this temperature from 384 to 100 degrees C. So if I put 100 degrees C in stream number 4, 100 degrees C, it will then calculate the duty, and then hopefully it will then calculate for us what is then the temperature in stream here. So I will then redo the how to call it, the simulation. Okay, looks okay, but it takes some time. FT correction factor is low, so we will then later on we will design it accordingly. Yeah, and I'll tell you. So we let this up until 100 degrees C, and then apparently from 33 it goes to 180 degrees C. 180 degrees C. Yeah. So it's not going to like that 200 degrees C or something that I calculated based on the assumptions of constant CP. So this is then the importance of making or evaluating the options that we have in the grid diagram directly into the simulation, so that we can have the overall performance if this option is implemented. So in this case, we for sure it's from 33 degrees C to 180 degrees C, and then it will then need, because we need to have the temperature here 250 degrees C, so we will still need this heater. But then in this case, we don't need to have this cooler. See, the duty is very how to call it? Why is this duty very big? Yeah, it's kilojoule per hour. I don't know. We have to then divide it by 3,600. It has some. I mean, in this case, it has some vapor to condense. Even the temperature is 100 degrees C. Even though the temperature is 100 degrees C, but then it has some vapor to condense. So apparently, there's a phase change over here happening. So even though the temperature is constant, we still need to have some energy, in such a way that it will then reduce the vapor fractions. But in this case, because of the thermodynamic differences, so we'll have to check the thermodynamic. So in this case, by not having this, for example, I would like to see, I put 100, 100, but then the temperature is, the vapor phase is increasing. You can see now from 0.09 to 0.1. So we are seeing this cooler, instead of cooling it down, it's heating up this stream. See, you can see the danger in this process simulation. So it's not allowed. So instead of specifying this temperature, I will then delete this. I will then specify this to be 0. So because this exchanger is not going to be it's not going to be doing anything. So I'll remove this pack. And then I will then put 0 in this exchanger. So that means we know that this exchanger is not doing anything because we are removing it from the equations. And then you can see we want to keep the vapor fractions as constant as possible. So it's like 0.1, 0.1. So that's basically what it is. Yeah. So that's how we evaluate what it's going to look like on the field as well. Because when you say you put this, for example, yeah, if you make the mistake, like you put these options over there, and then you forgot to evaluate what is happening in this exchanger, like I did, and then you come to your boss and then saying, and then you presented the results in the mass balance, and then your boss asks you what is then the vapor fractions over here, what is then the vapor fractions over there, and then you said, well, according to IC says the vapor fractions is increasing, and then your boss will then punch you in the face, because that is not possible, because this is cooler, yeah, not heater. Okay, so that's what it is. For evaluating the options. It says the FT correction vector is low. Yeah, it has something to do. Well, not has something to do. It has everything to do with how many tube passes and then shell pass, and then how many shells in series, and then the type of the shell. So this is then the thema type. So if you can still remember your heat transfer class, especially in the book of Kern, I don't know if you are using Kern textbook anymore for process heat transfer, or at least in Colson. So if you that graph, if you go back, so this book, this is then the Excel file that I mentioned to you. It comes with this book, and then yeah, it's not here. So there is the chemical engineering design, or from tolerance not now, chemical engineering design, I think. So it has, apart from Kern, that tolerance notebook, it has the various thema standard that you can select, or you can also Google the thema standard in this case. So you can then see what is then the tube passes. You can then calculate, basically. You can then calculate if you select how many tube passes, shell passes, how many shells in series, and then which shell type. You can then calculate from the inlet and outlet temperature that you want to have. You can then calculate how much is then the FT correction, which ICC is calculating it for you. So in this case, for example, if I put I don't know, maybe to see what happens. Now, if I put shells in series, that means it's more like I enlarge enlarge the if we put 2 shells in there, means it has to go, so this tube size going to 1 shell and then goes to another shell. So it's more like we are enlarging the heat exchanger in such a way that the TFT or it's not a problem anymore. Yeah, it is not a problem anymore. So that's how you tackle this issue. Okay, now you know then how to use this heat exchanger design. So quickly you can then say, well, if we want to design this exchanger, because this then a new exchanger is a new heat exchanger. So you can design it. You can tell to the mechanical engineer guy, 2 passes this that one cell passes 1 and 2 shells in series type E. You can also change type E if you want. And then it needs to have and then it will give you this amount of UA. Okay, obviously this some simple calculations, but it I mean it works in practice. So that's the how to get these options. Not really sure because it's almost 2 hours now. You can then try to put this stream there here and then retain this and then see if you can then reduce this duty further. You can do so. And then you can then evaluate, okay, how much is then the cost associated with that, how much is then the you have to find this cost in from the literature or from your in practice it will be coming from the department. You can use also Excel, how to HYSYS, because HYSYS has the they have the see capital cost, so you can I forgot to activate this, so you can then remove this and then activate that, and then you get the cost number, and then you can have this, and then you can also activate this, so that yeah, economics. No. I don't know why I cannot do this. Oh, it's still thinking. Sorry. No. Anyhow. Well, in the we kind of um, kind of cost. Yeah. So you could use this. I mean, you could use also your number to do the evaluations. Okay. I think I will stop here. I've shown you how to work quickly on what we should do. I will repeat that. Yeah. So you need to define the scope, and then once you define the scope, you go to the field. I mean, you go to the field when you get your mass and energy balance correct. Yeah, by using the process simulations or Excel or whatnot. Once you get the process mass and energy balance converge and then correct, and then you can then identify the stream, get the scope, get the mass energy balance, and then identify the stream, get the stream into one of these Excel file, calculate for you the target, get the scope, get the do the mass energy balance, and then identify the stream, and then you calculate how much is then the current or the base case of energy consumption, the hot utility and then the cold utility. In this case, the 6 megawatt of total heating, and then you get the heating. You get the hot stream and cold streams into one of these Excels, so you get to know the targeting of the minimum hot utility or minimum cold utility that you can achieve theoretically. So in this case, it's about 1 megawatt. Yeah, so that's why we know the 5 megawatts potential to be reduced. So with these examples, we have reduced well theoretically, and then you once you know the targets, you know how much you can reduce, and then you go to this diagram, and then you do your magic, see how much you can then reduce. So in this case, we can reduce almost 4 megawatt or 4.4 megawatt. That's what we can reduce by using, at least in this case, can reduce 4 megawatt theoretically using the assumption of constant MCP. But then when you apply these modifications, because this modification looks nice on the paper, once you get to the a more correct data thermodynamics, so you can then end up, instead of 4 megawatts that you recover, it's about how much was that? I think performance, I would say, performance. So it's Yeah, in kilojoule per hour. So you can calculate how much is that in kilowatts. So divide it by 3,600 something. So I don't know how much. So I don't think it's going to be like 4 megawatts, but yeah, you have to calculate this on your own, and then that will then be a more accurate cost saving figure that you can present. Yeah. So instead of present number, you can present, you should present, not you can present, you should present the value that you get from here, because assuming that we believe the thermodynamic model, and then it fits to the plant data, and then we believe this number much more than your simple assumption of constant MCP. I will yeah, so one option, two options, and then more than one options, more than two options. You can then do whatever you want with the options, and then you implement that into the real simulation or real mass balance calculations, and then you can then have a fair or more accurate cost saving figures, yeah, which you can then present to your boss. So I will stop here, and then we'll go to yeah, the Q&A session. Any question?
What an interesting sharing by the speaker. I believe our audiences are amazed by the versatility and abilities of an engineer. Now we move on to the Q&A session. If you have any questions regarding the talk, you may leave your question in the pigeonhole section in the multimedia reviewer at the bottom of your screen.
I saw a question, but it's too quick.
Okay, let us start with the first question for Dr. Zulfan. How often do we encounter threshold problem in the industry?
How often?
Yes.
Well, you shouldn't ask about that that question, because we don't know how often. Yeah, I mean, we will see that one way or the other, but that's not really an issue. I mean, whatever they call it, they call this kind of problems is threshold. Yeah, I don't know why threshold, but anyhow, it doesn't matter in practice. In academic, it may matter, but in reality, it doesn't really matter. And people don't care. So they call this like a threshold kind of problem. And then how often, I don't know. I mean, I haven't seen this in my, I don't know how many, three or four, yeah, somewhere around that plants. Never seen that. But then if I make like exams, I will put this as one of the exams questions. But nonetheless, the same approach. I mean, we apply the same approach. Yeah, I mean, so it doesn't really matter whether it's threshold, non-threshold, doesn't really matter. So what matters is that how much we can reduce from the current situation, how much money that we can save, and then how much CO2 that you can reduce. Yeah. I hope that answers the question. If not, then let me know.
Okay, thank you, Doctor. Moving on to the second question. Physically, a chemical plant complex is very huge. Is it practical to integrate the heat from stream located at the beginning with the stream located towards the end of the plant?
Yeah, that's then the practical question that we have to fulfill. If you notice, yeah, before I answer that, if you notice this one, I mean, it's see, if you notice this, eh, so I said to you before I go, I said to you that I typically use like hot stream is on here on the top, cold streams down here. So just to have like a consistent visual, that means heat is then being transferred from the higher location to the lower locations. Yeah, it's not necessarily because the temperature profile, I mean temperature axis is on the horizontal axis in this case, but nonetheless it gives us this feeling on the, yes, we can transfer heat from higher to lower, from the hot stream to the cold streams. But if you see this, yeah, so one hot stream region, and then another cold stream region. But if you see this, I make it 2, right? You can see. So I have this one region and another region over here. Both has hot stream and then cold streams. Hot streams and cold streams. Why is that so? Because these plants in practice, they are like more than a dozen kilometers away. More than 100 meters away. Yeah, more than 100 meters, which is quite far. It's quite far. So that's why this option 8, even though it is more, see option 8, it is then getting heat from one unit to the other unit. So this is very long. You know why this is option 8 as well? Because we did not, I mean, at least I personally did not prioritize heat transfer from one location to the other locations that is very far away. Because complexity may arise, all of the pipings, all of the pressure drops that we don't think about over here, it will then play a role. But then during the discussion, one of the engineers mentioned that we could do this. We could do this well, and then if they say they can do that and they're willing to do that, well, I'm okay with that. That's why this then the last option that we at the time we identified, at least I identified as the last option, but they knew this already. So this is something that we have to take into account, whether this is something that can be done or cannot be done. But I approach this cautiously. Yeah, in this case, as you can see, I approach this cautiously, that I don't prefer that to happen. But if you know if the plants are aware on the consequence, yes, then they can do that. Yeah, they know. I mean, it gives us the best solution basically. But this is prior to I think if I can remember that correctly, they've done a study in the past trying to figure out if they can recover this energy. They did as well, I think, the pressure drop calculations and stuff. So taking into account all of these new pumps and new lines, they think that's feasible. So it remains at the time. It remains one of our best solutions. So indeed, it happens, but you have to make sure, you have to be aware that it may or may not be profitable, even though the energy can be significant. I mean, the energy recovery can be significant, but it may or may not be cost-effective solution. Yeah, but in this case, luckily, it was one of the cost-effective solutions. Any other way? Let me know if that answers the question. If not, then let me know.
The next question is regarding the project that you identify the faulty heat exchanger. How do you determine it is faulty based on the overall heat transfer coefficient?
Very good. This is not something that they teach you in the class, but they, I mean, obviously in heat transfer class, you understand something called like overall heat transfer coefficients, yeah, the U value. So this heat transfer coefficient is something that is then found on the field. It's not something that you calculate. There are some estimations on that. You can calculate that basically 1 over U equals to 1 over H something. You can calculate that, but those are all empirical equations. But in practice, something that we have to calculate ourselves. So what we did, we compare the U value when you design this. Yeah, when you design heat exchanger, I don't know if you have if you have already a project to design heat exchanger. So when you design heat exchanger, we assume a U value, and then based on the data that we want to have, the temperature profile, we select a type of heat exchanger, in this case shell and tube heat exchanger, and then we can then calculate the U value. So if the assumed U value is the same like the calculated U value, you can then get a converged U value, which you will then use or put in the process data sheet. So that U value is what we call a design U value. So we compare that design U value, yeah, with the calculated U value on the field, because on the field, you know what the flow rate is based on the mass balance. If there is a flow meter, that's good. If not, there is a mass balance. You know the delta T in and out of the heat exchangers. That means you know how much then the heat is being transferred from one stream to the other. And then based on the delta T, you can then calculate how much is then the U value, the current U value. And then you compare that current U value with the design U value. So that's one way. Yeah, that's one way. And then you can then make a plot. I will show the plot. But then people on the practice, typically, if they don't see it, I mean, regularly they will do like a turnaround. they will do turnaround every 3, 4, 5 years, depending on the unit and then depending on the aging of the catalyst or whatnot. So when they do turnaround, they open these exchanges and they will see one exchanges, they have like a very foul situations, very oily, very so much solid in it. And then in other exchanges, they are very clean. So depending on the service, so they know that this exchanger is fouled, heavily fouled. The exchanger is very lightly fouled or no fouling, like intermediate fouling. So they need to put like a label because that's part of the job, so that they can know, they know which exchanger to focus on more cleaning and maintenance. So that's they don't do any these U value calculations that I've mentioned before. So they just simply during the turnaround they see it and then they yeah, they know falling, no falling, falling, no falling. That's the practical way. So but for you, because you are graduated from chemical engineering department, so you don't do that type of stuff. Yeah. So you have to calculate things because these things, they are data. So you calculate that. So before stopping the plant and knowing whether they are fault or not fault, you have to know whether they are fault or not fault before you stop it. So that's why you go to the chemical engineering department to study. So the way to know it is the one that I mentioned to you. And then you could also see the middle ground is then you can see the temperature profile. Yeah, if the temperature profile is then decreasing or increasing depending on which stream that you're looking at, then you will then see how much is that. I mean, whether it is fault or not. So what we did, the one that I mentioned to you, I think I put it here. So here, it's lucky that I put it there. So in this case, instead of U value, I put duty, because if you know that U value is proportional to the duty. So if the U value drops, the duty drops, yeah, and vice versa. So I upload in the time streams, and then because they have data on the like hourly or daily basis or whatnot, and then I calculate the Q being transferred from one stream to the other streams. So we can see all of this, the dots, thousands of hundreds of data, and put it in the dot, and then you can see there are more or less like having this kind of exponential decrease, right? So if I make a exponential equations on this, I will arrive at this line, red line. So this red line is about the middle ground of all of this scattered data. So that's the middle ground. And then that's how I know, yeah, because the duty keeps dropping. That's how we know that heat exchanger in particular is fouled. Yeah, that's the thing, that how you visualize what you have calculated before. I will add to that questions. In this case, once we know that that exchanger is fouled and then I identify it and then it was confirmed by the plant, and we dig deeper, how is then the profile. So we did for all of those fault exchanges, I made the same calculations like this for all of them. And then we discussed with the vendor who can claim that they can improve the performance of heat exchangers by 10% and 40%, even more, 100% or something. But then if I say, because all of this scattered data, it's impossible for us to get like a really insight and to calculate to get like a quantitative figures. So that's why I use this red line as a representative of ideal data. Yeah, it's not scattered, so it's really in the middle, and it's like the ideal situations. So if they say it's a 10% increase, then I will have to increase this red graph by 10%. Which is then the green one. So that's the green one, is then the improvement of 10%. Well, in practice, it will not be like a straight line, like the exponential line like this, but it will be like a scattered. But in average, it will be like this red line and then green line, and also this improved 40% is then the black line. So in here, the area in between the graphs are the saved energy, right? So this saved energy. So the energy that we can recover because of this improved performance. So that's the area between the graphs. So if you integrate that area between the graph from 0 until, I don't know, some 500 something, we stop at 3, yeah. Stop at 3 in this case, because we know it is heavily fouled already. So the area between the graph is then the something that we can then translate into the saving of the duty, and then the saving of the money. So that's how we know whether it's something fouled or not fouled from the data that we have on the field. So that's very important I cannot emphasize more on having the correct calculations of mass and energy balance. Yeah, so we have to make because in the plants here, for example, sometimes we have the flow rate over there, and then there's no flow rate anywhere else, and then there's temperature over here, and then temperature over there, but we don't know what's temperature in between over here. But they do have some temperature over here, so you need to get that calculations complete, and then you have to make like a sound assumption, something that makes sense, so that you can then have a feeling whether your data is correct, and then that represents the current situation. Okay, so once you know the data is correct, and then you can do further analysis. If not, then you better stop and then make sure that the data is correct. I hope that answers the question. Let me know if it's not, and if there's any other questions, please also let's discuss it, or we still have some time.
Thank you, Doctor. The participants have requested for the slides and the Aspen file from the tutorial session. I think our committee can personally message Dr. Zulfan to acquire the slides and Aspen file.
Yeah, I in return, I would like to have the recorded video of this. Yeah.
All right. Thank you. Okay, Doctor.
Yeah,
okay,
because we need to. I mean, we need to share this recording to everybody, so that you can always go back. Yeah, maybe many things that I've said now doesn't make sense to you, but if you then listen to that again, and then you get more knowledge, you do more cases, and then you come back to this recording, and then you can make some more sense out of it. Okay, more questions.
Okay, moving on to the fourth question. How do we actually calculate the heat exchanger data for the PBP index versus Kpax index?
PBP, pressure drop.
PBP.
Oh, T. Saying it. T or P?
PBP.
Oh, PBP. Oh, PBP. That payback period. Where is that stuff? Where did I show it to you? Oh, this one. Yeah, this one. What was the question again? How to calculate this? So in this case, we have like 8 new exchanges, right? And then we have our costing department, and then we know how much is then the energy cost, and then based on that energy cost, we know how much is then the energy that can be saved, right? Say for example that 4 megawatts. Remember that 4 megawatts that I mentioned to you. So assume that we can save that 4 megawatts, and then we can then calculate this 4 megawatts equals to, I don't know, 4,000 ringgits. Say something. Yeah, I don't know. 4,000 ringgits, and then we know that this 4,000 this 4 megawatt can be saved by adding one exchanger. So once we know what DT is, and then we design the exchanger, and then we can then have like a cost estimate. Either it's from the costing department or from the Aspen Energy, Aspen cost estimation. There's Aspen cost estimations basically. Yeah, and then you can use that figure. Then to get the investment. So that particular exchanger, the 4 megawatt one, for example, we will have to spend like, I don't know, maybe some amount of money. Yeah. So say for example, I don't know, maybe just put some number here, like 10,000 ringgit. I don't know. It's not correct number, but 10,000 ringgits. And then you know that you can save, for example, that's 4,000 ringgits per year or something. Yeah. So that 4,000 ringgits per year, you have 10,000 capex. So 10,000 capex divided by 4,000 per year. So that means you will have a payback period of about 2.5 years, basically. So 10 divided by 4. So that's very, I mean, that's the way we calculate a quick cost estimation on the payback period. Is that clear or not clear?
Okay, I think that's clear, Doctor. Thank you. Okay. Next question. In utility placement, is it practical to use multiple heating medium, or rather only one example to heat a stream from 50 to 300 degrees Celsius? Preferable steam and hot oil, or hot oil only?
That depends on what you have. Depends on what you have on the site. Typically, nobody else is now. How do you call it? Nowadays, there's nobody else is is then building a plant from the scratch means there is no utility, no nothing. Typically, if you want to build a plant nowadays, we build in an existing complex, and that existing complex, it normally has already the utility plant. So that utility plants already have some various levels of steam and then various levels of cold utilities. Well, cold utilities means in this case only like quick tower. But nonetheless, there are various levels of heating medium. And then if these various levels of heating medium comes with a different price, there where you have to be careful on which steam level that you want to connect your plant to. Okay, so if for example, so this plant is basically a complex in China. So there are various steam headers. Typically, we have like 3 steam headers typically, but in some cases there are 4 or 5 even. So high pressure, medium pressure, and low pressure, and then there's this low pressure condensate header. So there are 4 levels of hot utility in this case. So these are existing, which we can then utilize. So if they come with a different price, as in this case, it comes from a different price. And then that means we have to maximize the use of the cheapest utility first, and then go to the higher or more expensive utility. Yeah, if you somehow you design the plant from scratch, that's then the best way to design your own utility level. So please design it smartly, like what I've shown here. So there are many options here. So complicated utility systems already, from very simple like this, only one for hot, one for cold, and you can come back with I don't know, 2 hot, 3 colds, up to you, and many other options. Yeah, up to you. And obviously everything comes down with the cost. So it's depending on your cost calculations. If not, then try to make things much more sense. Typically, we divide the steam level by I don't know, depending on the requirement. Yeah, depending on the requirement. If it's like it's a very spread. If the spread you have like you need to hit something from to 100 degrees C, and also you need to hit something from something to 200 degrees C or something. So it's a 100 degrees C difference depending on how much they are. So it can be like a 2 steam levels, or 1 or more than 2, up to you. Just make sure that the cost is okay. Is still beneficial.
Okay, thank you, Doctor.
You're
The
welcome.
next question is there any problem if the temperature difference in the heat exchanger is very big?
Okay, so now what is then the problem? The problem comes with if the temperature difference, because well, we have like a hot and cold region, right? Hot and cold region. And then they typically, to save cost, we will then try to make use of these temperature differences. So for example, one stream is that not very cold. I mean, also in the manufacturing part, yeah. So if you say that you want to have like one is then at lower temperature and one is then at higher temperature, as of that we have the cold and hot stream, and then depending on the temperature, for example, if they differ too much, we will have what they call, this one is mechanical engineering, people can tell you more about that, but for us, we will see like there is a thermal stress, what they call a thermal stress. So we have a very high temperature on one side and then very low temperature on the other side. So we have a thermal stress. So this thermal stress may not be good for the material's lifetime. Yeah, so that's one thing. So depending on the fluid properties, depending on the temperature and pressure that you are dealing with, so the selections of that particular material is going to be costing you money or saving you money. Yeah, so this is something that you have to discuss with your metallurgy guy and then a mechanical engineering guy, but something that you have to be careful about. That's one. And then another one, instead of also thermal, we also see, like, for example, from the properties of the fluid itself. If, for example, you have a very cold fluid, or maybe the fluid is very viscous, and then that part on the higher temperature part is that you have a very either one. Yeah, assume that the higher temperature part is then the one with the viscous fluid, and then this then your cold medium. So on the wall where the heat is being, when the heat transfer occurs, because heat is then transferring from the hot part to the cold, but on the wall, because this part is cold, right, and then that part is hot, and then you can see, not you can see, you can calculate even. So the for the hot on the wall, the temperature is going to be very low because it's very viscous, relatively very viscous, and then the temperature is going to be very low. That means this how do you call it? The fluid, the hot fluid on the wall is going to be like a sticking out. I mean, it's sticking on the wall. So it will then give you additional layer of fouling. So the more viscous the fluid on the hot part, and then the higher the temperature difference between the hot and then the cold, the fouling layer over here will be thicker and thicker. If we have a thicker fouling layer, that means we will then reduce the heat transfer from the hot to the cold. So that is then another implications of having if we have too high temperature difference. So it has something to do with this, with that fluid properties. So two things, yeah, the material, thermal stress, and then the heat transfer itself. So that these two consequences, these two consequences are the things that you have to think about. Yeah. There is no right or wrong answer. There is no answer. Basically, I'm just just letting you know that these are the consequences that you have to be aware. Yeah. Because nonetheless, in the school, you are taught on the how much is that heat transfer, how much is then the U value, and so on and so forth. So there's very I mean, that's very basic question, but in practice, that is not the question. The question is then, can we make it work? So these are the two things that you have to think about on how to make it work from the process perspective and also from the cost perspective. So we cannot make like a very high alloy, very expensive ones, just simply to cater the huge temperature difference between the hot and the cold, which means that it can then kill you with the money. You have to pay a lot more money. It's also like a heat transfer part that is going to give you a problem. So I'm not really sure. Let me know. Yeah, that's what I can tell regarding that. But whether or not you have to do it, it's up to you. If you have more money, then you can do it. Rich people can do whatever they want, including in this case.
All right. So the final question is, what is the most concerned problem in the industry regarding process integration, and how do you solve it?
Good, excellent. I mean, why this is the last question. We could have 10 more questions if you want. Okay, so the most constraint process integration by I mean, go back to the first slide so that you can see. Well, I don't know if I go back to this first. So, for example, in this case, there is no put it here. I'll show it here. Before I put this, all of these streams are living happily, right? You know what I mean? So I want to increase the temperature, reduce the temperature. I can do that. So all of this coming from the utilities. You can just open and close utilities, the valve, right? Or if you want to have more steam, open the valve steam. You have more. You have to destroy your energy, destroy your cost, and then you can just open the cooling water line. So you can, I mean, the process can be controlled in a much better way. I mean, it's very controllable in that sense. But in one sense, we see that it's costing us money. So by adding this guy, the consequence is that we are now need to make sure that even though it says that it can recover the heat as much as possible, but we need to make sure that we need to have like a guarantee in this case. So this guy will have to work, and then this guy will also have to work, even though that we say we don't use this anymore, but it has to be there because the temperature here, it cannot be, I mean, it has to be like 100 degrees here due to whatever reason or the process reasons. So if this fails, if this faults, for example, if this exchanger faults, that means the temperature over here will be higher and higher. Yeah. will be higher and higher. That means we'll have to still run this exchanger in that case. So so from that perspective, we need to have better control of the situations. Yeah, we need to have a better control of the situation. So in practice, what they do is that they typically like bypass this exchanger. So if they want to maximize the heat recovery, they will just close the bypass and then and then let everything runs through this exchanger. But if they want to make some controls or whatnot, they will then do open and close the bypass valve in such a way that they can really control. So that's simply that additional control simply comes from the additional this one guy. So imagine that you have another guy over here. You put it over there, and then another guy somewhere here. So the more complicated the solutions that we give, I mean, the more integrated the plant. That's a correct way of saying it. The more integrated the plant, that means the more the controllability space is going to be reduced. Yeah. Before, we can just simply open and close the utility valves. There's no controllability limit other than the valve control valve itself. But then the more integrated the plant, the more control system that we have to put in place, and then it has to be more. Yeah, and then the more complication it has, the more sophisticated all of this control system, and they I mean the what do you call it, the frequency of it fails is going to be needs to be like a reduce and reduce. So that is then the complication issues that arise from having more and more integrated plants. But having more and more integrated plant, in one sense, it can cost. I mean, we can save a lot more money. We can reduce a lot more CO2 emission, but we have to pay it with a better control system, a better human capability, because in the end of the day, it's all humans who are going to operate these plants. We are no longer there. It's not that plant is going to be operated by a robot. If we can, yeah, well, we'll have to do it to minimize all of these errors. But I hope you get the idea that the more complicated, the more integrated the plant is, the more integrated the plant is, the more complicated control structures that we have, the more how to call it? Yeah, you need to have like skills with the higher skills. So I've seen plants. I've seen many plants. So basically, so some plants with a very how to call it, very simple, and then they don't any. I mean, they can just run it without even thinking. But then for the plants that have a very sophisticated control systems, they cannot hire the same level of people, so they need to hire people with a higher level of educations. They need to give more trainings to that people, so these people working in that complicated plant will be different from that people working in a very simple plant. So so these are the things that we have to be aware of. Again, there is no solution that fits all the problem. Just something that you have to think about, and something that we have to work around it, as everything else in life. I hope that answers the question. If not, then let me know. If there's any other questions, you can always ask me.
Thank you, Doctor. To all participants, if you have any other questions, you can type it in the chat box, or you can unmute yourself. Can I hear some feedbacks from the participants if you have any other questions?
Closing this without saving it, so that all can look it in the original fashion.
I think there's no questions from the participants, no other questions, right? So with this, our Q&A session has ended. A big gratitude to the doctor for the response to the participants' inquiries. We appreciate the information you have provided us with, and we acknowledge and value your prompt reply. Thank you for the inspiring and electrifying sharing by the speaker. Ingenious with versatility will have a strong ability to contribute to the society using their wide range of skills and knowledge in their careers. We hope that this talk session has inspired you to continue striving for more technical skills and knowledge to become a better engineer in the future. This marks our industry